But now I do want to introduce David. And once again, I mentioned earlier, very thrilled that you can join us because I know that you have been studying all things ventilation and air cleaning wise with respect to the prevention of COVID and particularly from schools and other environments where people can't control their own environment. So I just want to introduce that Mr. Elfstrom is an independent engineering consulting on efficient use of energy in buildings, including ventilation systems. Earlier this year, Mr. Elfstrom completed a ventilation and air pathways assessment of an apartment building in a COVID-19 outbreak for a public health unit in Ontario. He is a member of the citizens advocacy group Masks for Canada and has been helping the worldwide grassroots effort to design and build do-it-yourself portable air cleaners, of which we are fans of those too. So he's going to talk about deploying the anti-airborne engineering controls of ventilation, filtration, and UVGI. So you can tell us what the acronym means too. Thanks.
Sure. So I'm going to, let's see if that works. So I'd like to talk to you this afternoon about three main ways to rectify poorly ventilated spaces. And by the end of this presentation, you should be able to confidently recommend ways to improve indoor air quality. So I'm going to cover three different sort of topics. The first is just a basics of ventilation and what it really is, and some simple ways on how you can improve a system. Second, I'm going to talk about filtration. That'll probably be the bulk of it today. And then at the very end, I'll have a shorter look at germicidal ultraviolet light. So what is ventilation? Ventilation is the minimum amount of outdoor air that's required to control contaminant levels. Standards for ventilation are based not on health, but on minimal dissatisfaction. And it's basically based on ventilation rates for acceptable indoor air quality is based on the number of people being not dissatisfied with the air quality. The main ways that you can do it is it can be natural, such as by having open windows, or mechanical, and that's usually a supply fan bringing air in, and an exhaust fan drawing it out. It could be either of those two or both together. But fundamentally, it's all about pressures. Air moves with pressure difference. Wind can create a positive pressure on one side of a building, negative on the other, and that will cause air to flow through the building, through small cracks, and through intentional openings. And temperature difference creates a density difference, which is a pressure difference. So temperature differences also cause air to flow through openings in a building. And that's why you get far more air exchange on days when there is a greater temperature difference between inside and out, regardless of the wind. And any fan or blower works by creating a pressure difference. So it's all about the pressures. One of the big questions might be, well, how do you determine if a building has poor ventilation? And you can look for some clues. And the age and type of building has a great deal to do with that. Before 1990, Ontario buildings that were sort of Part 9, which is sort of residential style, small commercial buildings fall under that as well. They didn't really need to have any mechanical ventilation at all. And you'll find that homes didn't even need to have exhaust fans in bathrooms as long as they had a window that could open. My home's an example of that, built in the late 60s, early 70s. But this also extends into retirement homes that were built mid-1980s, no ventilation, and that becomes a high risk factor for disease transmission. And as we've sort of talked about briefly, you can spot check with carbon dioxide for short-term logging. So let's look at a simple sort of small commercial system. These units are everywhere. this is a very simplified diagram. So there's a rooftop unit. They're on strip malls, they're on daycares and paint stores, optometrists, framing stores, bookstores. They're the long tail of buildings that are out there. And this is one area that seems to have been overlooked in communication about ventilation, because every time I go into one, there's usually some issue that I can quickly identify. The operation is in the hands of the tenant of the building. And there's a simple control, just like a house thermostat. But essentially, it's always providing, as long as it's running. So essentially, we're looking at a box on the roof that is recirculating air. It's taking return air from sort of an egg crate style of grill in the ceiling, mixing it with fresh outdoor air, filtering it, and then distributing it to the rest, heating it and distributing it throughout the building. So that's the simple part. The main issues here is control of dampers, which I've shown as these little louvers on the side, that those allow variation in the amount of outdoor air that's introduced. And as you introduce more outdoor air, there is a relief valve at the bottom that can send out the excess stale air. The main issues here is that they're usually set to auto. And whenever they're set to auto, it means that if the thermostat is satisfied, then the whole system doesn't run. Great for energy savings, but that means you have no ventilation. So it's very common to go into a small commercial building. Doesn't have to be a commercial building, it can be any type of building that's about that size, and find that it's set to auto and it's all satisfied, and the CO2 level readings, if you happen to bring one, are going up and up and up. Other things that you can do to, once you've switched it into on, so it's always running, is make sure that the fan belts are tensioned properly. That's a big issue that's not mentioned most of the time. We find that once the belt is replaced, it's supposed to be retention, but it isn't, and you get belt slippage, and then it's actually delivering much less fresh air than intended. Upgrading to a higher level of filtration to a MERV 13 or preferably MERV 14 filter is also highly recommended. So that leads us to filtration. The question is it not, oops, it disappeared, I can't see it now. Yeah,
would you rather have the questions at the end, or do you want them in between?
I like them. Well, it's actually okay if I can. It's just that it's taken them away from me because I used to be able to see them.
It's difficult to see when you're presenting. That question was about, in this diagram, isn't it not advisable to have the air exhaust vents right next to the outdoor air intake vent?
That's a good question. They are actually right below, and it depends on the design of the unit and how they work. The other issue, well, it's not so much an exhaust as it is a relief valve. So if you have point exhaust in other places in the building, it's going to be coming out of there. It's coming out of the bathrooms. This is just more as if you are increasing the indoor air, it's going to, as you're increasing more, you're pressurizing the building with more outdoor air, that's a kind of a relief valve to let it out, to the excess out. So it's a much smaller amount. And then you're also filtering it anyway as the fresh air is coming in. So the other, the other type is, well, a building that's even older and doesn't have any kind of ventilation. Those are the ones we're very concerned about. They may have exhaust-only ventilation, in which case it pretty much you have to rely on open windows for bringing air in and ensuring that that exhaust fan is running all the time. And in those situations, it's almost essential that you need to have a portable HEPA filter. And I've drawn on here a split system AC. Many people may think that that's providing outdoor air, but it's not. All it's doing is recirculating air within the space, not really providing any measurable amount of filtration, but it's making you feel more comfortable. I think I'll just go to a blank slide. Well, no, I'll go to the next one. So filtration. There's three mechanisms. Well, I'll say two mechanisms that we're really concerned about. Filters don't sieve out particles. Well, they do if they're extremely big, but that's not how filters work. They work on a much smaller scale, and it depends on the size of the particle. This is a diagram showing a regular, typical filter that you might find in a furnace. And the really small particles are captured by diffusion, and then the next size up, around the 1 micron size, are captured by interception. And the two together create this sort of valley-like curve. And that same curve applies to all types of filters, to the point that when we talk about HEPA filters, it's right at the top of the efficiency, but there's still just a little bit of slightly lower efficiency at capturing at a particular size. And so they're usually designed at around 0.3 microns is the design point for the performance, but it may be a little bit less. So in this case, it's showing a HEPA filter is only 99.94% effective at the 0.2 micron size specifically. So this kind of addresses that myth of when someone says, oh, HEPA filters only filter down to 0.3 microns. No, in fact, they're actually even better at 0.1 microns, around the same size as a naked virus. The virus doesn't actually exist naked floating around in the air. It's in larger respiratory particles. The actual size of that, it's still under debate as to what the distribution is, but it can be in the range from, say, 0.2 all the way up to 5 microns, even bigger as well. But they all are captured to some extent by these filters. So when I'm talking about MERV-rated filters, it's a standard for rating filter effectiveness with size. It's established by ASHRAE in one of their standards. And if we look at a MERV 13 filter, so the naked virus is around 0.1. But the size of respiratory particles that we're often considering as dominant is actually in the 1 micron and up size. So it's effective. So a MERV 13 filter, which you can actually buy and install in your home, is getting upwards of around 90% effectiveness at filtering out what we believe is the majority of particles containing the virus. Even so, if they're not, they're still in this range here. Even at the worst point, it's still filtering out 40%. So if you pass the air through twice, you're filtering out 40% times 40%. You can continue to filter. So in that regard, that's why a homemade air purifier, well, it's not showing me, maybe you could see it in the small view, that moves 4 times the amount of air can still be just as effective at cleaning the air as a HEPA filter, which may be 99% effective in a single pass. And there's one other myth that I think I should bring up. There's concern about moving the air and causing transmission because you're blowing the air around. Well, that's exactly how ventilation works. Ventilation works by moving the air around, diluting it, and thereby cleaning it. Filtration works in the same way. You have to move the air to filter it. And there's many subtle air currents always moving. We just can't sense it, but you can tell they're there. You walk slowly past a desk and your papers fly off. That's not an insignificant air current. It's always moving and stirring, and we've got a plume of air that comes off the top of our bodies and moves up, and it's always stirring and mixing. There can be dead zones where it's not effective, and can have a buildup of material of aerosols. So I can move on to upper room germicidal irradiation. So this, for some reason, let me get rid of that annotation. Okay. You may have not heard about this that much. I consider it to be one of the three main ways of addressing airborne transmission indoors. And it can take, it's essentially using, it's a mature technology. It's been around for 70 years. It's been used in schools to reduce tuberculosis and all sorts of other places. It's proven technology. Essentially, 265 nanometers is the optimum wavelength of light to damage DNA and RNA. Now, our technology, in terms of the tubes and the way they fluoresce and the spectrum of light they put out, it's actually 254 nanometers. It's pretty close. So they're very effective at that range. There are some newer wavelengths that are being able to be created that are a little more safer as you get to a smaller and smaller wavelength. Around 222 is coming as products come in. It's not as effective at damaging RNA and DNA, but it's also a little safer as well. But essentially, you want to keep these, you have to have at least a minimum 8-foot ceiling, 8.5 foot preferred, and it's going, any amount of aerosol that gets up into that zone instantly, effectively, is not going to be, it's sterilized. So it won't affect you. It can create the effectiveness of 10, 20, 30 air changes per hour with just that. So it's ideal, though, for spaces that have larger volumes where you can't filter as frequently or as easily, such as cafeterias and gymnasiums. It's perfect for bars where people are actually singing and shouting and creating more respiratory aerosols. And the other type is induct. So there's the two types, induct and upper room. Upper room is easier as a retrofit. Induct has to be designed properly. It can be a little more cost effective, but you need to have enough of a delay in the air. It has to have enough exposure time as it's moving by for it to be for it to work properly. And so it does require engineering. The cost of in-room depends. I haven't seen it many installed, but it's for a classroom, you have a couple of different options, but you're going to be installing probably 2 to 3 units in a typical classroom at about $2,000 each, so maybe around $6,000 per classroom. They're also available in a pendant style that can be hung just like a light fixture, and they can even have little fans in them that help assist the air movement throughout it. So I think it should be much more common. And it definitely has a role, especially in those larger volumes and higher risk areas. So I think that's a good conclusion. You might have a lot of other questions. I'm happy to entertain them. But yeah, the question, how long do the bulbs last? Depends on how long you run them, but kind of similar to a regular fluorescent tube, maybe about a year or so, year to 2 years. And good question. There are new LED type technologies that are coming out, which should last longer, but they generally tend to have less radiation output or less light output that can actually do the job that's needed. So for now, we know it's proven technology. It's been used for many years. It does work. We just need to implement it. So now that you understand some of these engineering controls, hopefully you'll be able to see how they could be implemented to reduce the chance of airborne transmission in buildings, especially outside of healthcare, where they're already being implemented. And generally, these upgrades can readily improve air quality at the cost much less than plexiglass and far more usefully as well. So That's the end.
Great. Thanks, David. There's a few more questions about the UVGI in terms of, well, the hazard presented by the light. So I think, so one of the questions, do they need to run when no one is present because are they a risk to the occupants? And then, or can they be incorrectly installed, presumably therefore a risk to the occupants? This is sort of
Yeah, there's so they have louvers on them to keep it at that level, so it's not straying around the side. Some may even have extra. If there's a concern that people are actually going to be in that zone, there's also safety controls where it can instantly shut off when something crosses a beam. It's other ways are actually, once they're installed, you can have an actual UV sensor, move it around the room, and actually measure the level of radiation exposure in different parts. So it does need to be done safely, but it can be done safely. So
interesting. So have you like been involved in such like in testing them kind of thing? Or?
No, I haven't. I haven't had the opportunity to.
Technology, but it's interesting. So there's a question on commenting on how barriers are now being questioned as being counterproductive, as in causing airflow disruptions or making ventilation less effective. Do you want to?
Yeah, for sure. It's simple fluid mechanics is you create. It happens in buildings. It happens anytime you create, you have a wall. Essentially, anytime you have flow over like a weir or a barrier, it creates an eddy that just traps contaminants. Mm-hmm. So as soon as you're erecting them, you're now changing the airflow, because typically you have airflow coming in out of a supply register, moving across throughout the breathing zone, and then going back up. So as soon as you stick something in the breathing zone, you're just trapping it in there and it can't get out. So, yeah. Yeah,
so it's a particular hazard when more than one person is sharing that breathing zone, right? Because then they're sure. Trapped together. If it's only your own breath, I guess. But it's not a telephone booth either. But so another question is UVGI the recommended method for large manufacturing site that only has space heaters and no AC? So no, I guess no mechanical air movement. So would UVGI, do you need the air movement part of HVAC to help with the effect of the radiation?
Yeah, you need some air. You need some natural air movement, and that can be enhanced with fans. Very often in manufacturing facilities, there are the big ass fans, as the brand name is, that are used to destratify and move the and circulate the air around. So some amount of extra air circulation like that can make it much more effective. It will still work anyway, but yes, you do want to have at least that breathing air zone mixing. And I have seen some giant, essentially the same version of as the small little Corsi box. Corsi Rosenthal box, but with a massive blower and giant panels for creating large amounts of filtration in an industrial setting. It's just that it's noisy.
Yeah. Steph did comment that they have 6 big ass fans. The person who asked the question about the manufacturing. So, and yes, the comment that the barriers are a holdover from droplet. Oh yeah, they still are.
Yeah, I said when you're talking about installing them in a bar, the only type of bar they should be installed on is a salad bar.
Mm-hmm. Yeah, that's true. I had a couple of questions actually. Well, one related to the passive airflow in buildings, and I guess we were actually talking when we were doing the workshop this morning. That is that about 0.2 air changes, or how, I guess, is there a number one infers, or I guess the temperature dependence I hadn't thought of. Is there any place to go when we were trying to use the calculator, any place to go to do a guesstimate of that in terms of CFM? Obviously it depends on how many leaks in your building, and if you have an exhaust fan, I guess, running, then that, well, sorry, if you got an exhaust fan, that's not passive.
Yeah, there's two For ventilation, you mean just sort of passive natural air changes that
Yeah,
occur
yeah.
due to air leakage? It depends on the height of the building, the temperature that's,
Stack effect, right? Yeah.
yeah, you can get a stack effect that can actually be quite effective at moving air unintentionally throughout the building. So the higher you go, the more it is.
Hmm.
But we try from a building science perspective to seal the building envelope for durability purposes and then ventilate properly.
Hmm.
But natural air changes per hour, yeah, around, depends on the size of the volume of space too. So zero point 0.2, zero point 0.4 air changes per hour is kind of normal for regular outdoor air movement and temperature, but it really varies. You get a lot more in the winter with a cold wind and great temperature differences compared to a stagnant summer or spring day when it's almost the same inside and out and there's no wind movement. So you can have basically next to nothing. Or you can have a fair amount on a windy day if it's a leaky building.
Hmm. I was interested, so I obviously talk about this all day, but that there was speculation that there was some kind of an air inversion affecting that restaurant in Oslo, where they had that incredible outbreak of, from a whatever Christmas party of the Omicron outbreak, and there was some speculation that the rainstorm or something that night had actually obviously, well, anyways, it had affected the ability of the restaurant to evacuate any of the air.
It's possible. We do know from the studies that have been done on arenas that you get a whole layer that just sits above the ice and does not move.
Yeah, yeah.
So the temptation is for me to strap the CO2 meter on the back of my daughter's head when she goes for skating, but I don't.
An additional incentive to stay upright, I guess, right?
Yeah.
So, don't breathe close to the ice. Kevin, yeah, you had a question or comment?
Yeah, it was something we were talking about the other day. What can we do in our homes? And we might or make a do-it-yourself Corsi Rosenthal box for our own house. But we're talking about filtering the air. And I'm not from Canada, I'm from Australia, so furnaces are kind of new to me. So I don't really understand the whole recirculation process. But I know we do take outside air, we do take inside air, we put it, through a furnace to warm it. What's your thinking about like putting a MERV 13 in the supplier for houses? I know the last thing you want to do is increase the back pressure because you're putting extra pressure on the furnace. But I just would be curious to know what you think about that.
Thank you for that lead-in. In Canada, we mostly have 1-inch filters, so you can buy these just about anywhere. This is a 1-inch MERV 11 filter, and this is a MERV 13 filter. Now, here's the interesting thing. Look at the difference between them. The MERV 13, far more surface area.
Right.
The MERV 11, not so much. And on the back, it's actually got these things. It's got the extra cardboard that also restricts flow. It's kind of flimsy. It's not too strong, but it's cheap. It will filter reasonably well. MERV 11 is pretty good. This filters a lot more. It's MERV 13. It actually says on it how much it filters at the different particle sizes. But here's what's interesting: the airflow rate and the resistance of the filter. This has lower resistance to airflow, which means you get more of it than this one.
Yep.
So you actually will get more airflow and cleaner air in your home by installing this one. Now, that's not generally the case for the thicker filters. It's just that this mini pleat filter is just fantastically designed, and I think it's great. But if you go and see a MERV 13 filter that looks like this, and it happens to be a lot cheaper than this one, it's going to have a lot less airflow through it than even.
It's called a mini pleat, did you say?
I call it a mini pleat because it's really, really fine. It's a very fine. It's many pleats within a given area.
I was
You can't
wondering,
expand it out. It's actually quite a large area. Now, when you talk about more like the commercial size, commercials are usually around 2 inches and bigger. And this is a MERV 13 commercial filter, and it has about the same amount of airflow as that mini pleat one that I just showed you. But this generally we don't have this for our furnaces in our homes. But this is the type that are being installed everywhere in schools and in offices and other places. So that's what it looks like. Same sort of idea.
my husband just bought some of those to make a Corsi Rosenthal box. I was going to ask you about that. I assume that it would be equally good, I guess. But
Yep, both of those two are essentially equivalent.
and
I just showed you
Jen
that.
popped in, and great to see you here, Jen. Is that a 3M 1900 in Canada? Is that what?
Yes, yeah, the 1900 is the MERV 13 with
Right.
the best performance per filtration sort of effectiveness.
Right.
There's a little slightly higher one that's even much more expensive, but actually is a little more restrictive to flow. So
It's the best balance.
generally homes in Canada suffer from the lack of airflow. So we want to try and change the filter regularly because that will reduce the amount of airflow when it gets clogged up. So every 3 months, change these filters for sure.
Thanks, David, and you're sticking around to the end. So if anybody has any questions.